land ocean wave models, numerical analysis, model diagnostics, and analyzing and interpreting geophysical data and model result. Dr. Mehra has taken on the responsibilities of providing key science and technical leadership and supervision to help build the coupled modeling and then data assimilation component and framework for the future operational system at NWS NCEP. As chief of the dynamics and then coupled modeling group, Dr. Mehra has been active in two major focus areas of research and operations at NCEP EMC, which deal with coupled models and the data assimilation. The first area is the global systems for medium range weather, S2S and oceans. And the second one is the regional systems for hurricane and tropical cyclones. So he is going to present the hurricane analysis and forecast system that's been under development for a few years. Please welcome Dr. Mehra, and Avichal, please, whenever you are ready.
Thank you so much, Young-san. Can you hear me all right?
Yes, we can.
Yes.
Okay, can you see my screen?
Yes.
Okay, great. So thanks for that introduction. Welcome all. Good afternoon. Good morning, perhaps, for some. So today I'm going to talk about the Hurricane Analysis and Forecast System, HAFS for short, which is being built as a UFS, a Unified Forecast System-based hurricane application. This talk, I've gotten a lot of help from Dr. Shujin Zhang from HRD at AOML in Miami. Shujin and me, we are the designated co-leads for this UFS application. And the content of my talk here is based on a lot of hard work which has been done and is still ongoing by EMC's hurricane team members, as well as a whole plethora of our active collaborators at AOML, DPC, NCAR, National Hurricane Center, NOAA Labs, GFDL, ESRL, as well as some of our academic partners at FIU, Oklahoma, and some private players like AER as well. And the team which has been put together here is quite extensive. And to be very frank, I struggled in picking out the highlights from all the useful, productive, and very advanced work which is going on across the UFS enterprise to help us build this next generation hurricane prediction model. So talking of hurricanes, officially the 2020 Atlantic hurricane season ended just 3 days ago on November 30th. And by any measure, this was an extremely busy season. In all, we had 30 named storms, and 13 of them turned into hurricanes, 6 of them into major hurricanes, which means Cat 3 or higher. 12 of these hit the U.S. coastline, 5 of them in Louisiana alone. And of these, 10 were rapidly intensifying storms, which is, of course, one of our primary challenges in context of hurricane prediction. Also, in terms of our observational assets deployed within NOAA, we had 86 missions conducted by the hurricane hunters, total flight hours approaching 700, and more than 1,700 drop zones were deployed in these missions. We also had a lot of hurricane glider missions, 47 in all, collecting close to 180,000 temperature and salinity profiles, as well as we had recourse and access to data from 16 NOAA weather service satellites, NOAA weather satellites in operations. This was a 5th consecutive above normal season, and National Hurricane Center participated in 86 Facebook Live broadcasts covering the entire season. Okay, so I'm going to start by acknowledging all our major partners working on HAFS as part of within our UFS framework. So it's NCEP, EMC, AOML, Hurricane Research Division, Geophysical Dynamic Lab in Princeton, Earth System Research Lab in Colorado, 2 parts, GSD, as well as NESI Group. Our partners also at AOC, as well as Development Testbed Center, DTC. Here's a brief outline of some of the topics I'm going to cover, introduce the application, then talk a little bit about our strategy and our science objectives, and then talk about what we have so far accomplished in years 1 and 2 of development of this application, and then what we think the targeted initial operational configurations will be for HAFS going forward, and end by talking about some ongoing developments and challenges and our future plans for the next 3-4 years. So as I mentioned, HAFS is a UFS-based application. So what does that mean? What that means is that in the schematic here are shown all the different major modules of UFS. It's a schematic which covers everything which is being worked on in UFS infrastructure. And the modules which are colored pink here, are the ones within this UFS framework which are being worked on, are contributing to the development of this hurricane application, or HAFS. Also, what is also important in this context, and especially from an operational perspective from the Weather Service, is that HAFS fits in with our ongoing efforts at NCEP, at EMC, to simplify our production suite. So currently we have 2 operational hurricane models, HWRF and HNMMB, or which is also called HMON. And we are moving forward and plan to replace both of them with HAFS. This Gantt chart here lays out some of the timelines associated with development and then operational transition and implementation of UFS-based applications. So for HAFS version 1, as indicated by the yellow arrow here, we are targeting Q3 FY22. So this will be one of the first UFS-based applications to be implemented in operations right after the moratorium ends. The moratorium is currently planned to start in Q3 of FY21 and last 1 year. So in terms of our strategy and science objectives, starting with the Weather Research and Forecasting Innovation Act, which was proposed and then ratified by the US Congress in 2017 and 2018, lays down the groundwork for our next generation of HFIP. HFIP stands for Hurricane Forecast Improvement Program, and HFIP has been in existence for almost a decade and was key in developing and improving our operational models, HWRF and HMON. So with this act, the next generation of HFIP has been recognized and ratified, and we have been asked to build upon the original goals of the project. And some of the new specific goals and metrics are outlined here, listed here. So some of the metrics which we are going to measure our progress by is to reduce our forecast guidance errors, including during rapid intensification or RI, by 50% using 2017 as our baseline. Produce 7-day forecast guidance, which is as good as the 2017 5-day forecast guidance. NHC and other forecasters are actively looking at extending their warnings from 5 days to 7 days. Improve guidance on genesis of pre-formation disturbances, including the timing and the track and intensity forecasts for that by 20%, again using 2017 as a baseline. And also improve our hazard guidance and risk communication, use the best social and behavioral science tools to modernize our products, which can then allow for better and more efficient actionable lead times for our emergency managers for storm surge and all other threats related to tropical cyclones or hurricanes. And a key part of the strategy is to develop and advance the hurricane analysis and forecast system so that we can bring in the next generation HFIP science and research to operation challenges and address them as part of HAFS. So as a UFS application, HAFS is based on FV3 dynamical core, just like all other atmospheric models within UFS infrastructure. This is a multi-scale model, and with data assimilation, so that we can provide tropical cyclone, hurricanes in the Atlantic and East Pacific basins, and typhoons in the Northwest Pacific Basin, for example, analysis and forecasts for the inner core structure of these storms as well as for the large-scale environment. The HAFS development is targeted towards an operational system for these forecasters, for our tropical cyclone forecasters, and give them reliable, robust, and skillful guidance on storm track and intensity, including RI, storm size, genesis, surge, and also associated rainfall and tornadoes. And HAFS, along with the operational requirements, is also being designed for cutting-edge research in tropical cyclone modeling, physics advancements, data assimilation, as well as coupling to other Earth system components for high-resolution storm predictions within the NGGPS strategic implementation plan objectives, which had been laid out earlier for the Unified Forecast System. So continuing on with our strategy, we are looking at using cloud resolving resolutions with nesting, using static nests, and when available, telescopic and moving nests, both within the global and basin-wide domains. We plan to improve our physics schemes by using observations, available observations, whatever is available now, and also try to use any new observations or new information coming from observations in the future to enhance our capability of simulating the physical processes with more accuracy, advancing our inner core and satellite data assimilation algorithms for tropical cyclones. And as new observations become available and new DA algorithms are built, especially as in context of JEDI-based infrastructure, we hope to deploy those as well. In terms of our forecast priorities, improving the prediction of rapid intensity change and track of hurricanes, improving the forecast as well as the ability to communicate of potential threats like surge from hurricanes, and incorporate risk communication research to help create more effective watch and warning products for the general public. Okay, so now I'll be talking about some specific accomplishments, starting with accomplishments in year one. This was for 2019. We set up a code repository, and we have set up HAFS management of that code repository using GitHub. More about that in a little bit. We have functional workflows which continue to evolve. More about that later. We also working towards having all kinds of nesting capability within FV3 DICOR, which involves multiple static nests. And this is the first step towards moving nests in the future. Exploring a number of physics suites within HAFS framework. And year one, we also designed and used multiple HAFS configurations. A couple of those which we used in real time included regional static nests, and also these regional static nests within global FV3. So some of the highlights include, as I said, having the code repository and management. We set up an authoritative HAFS repository on GitHub with the address shown here. And we're following a typical structure, which is recommended for community code development, whereby we have the Git flow rationale of having branches. We have develop branch for major developments. We have a master, maintain a master and gold standard, which under web version control, which is to be used for experimentation. And then we also have feature branches. And we follow the Git flow strategy to bring on developments and advancements from the different forks into the master, and then sync up with all the parallel developments. One other thing which I mentioned, which we worked on year one, was to have the ability to do multiple static nests on multiple tiles of FV3. So an example is shown here, whereby we've added two more tiles, tile 7 and tile 8, which are as part of FV3. We were able to do this successfully and get bitwise identical results using the baseline FV3 GFS code. We were able to do 168-hour or a 7-day forecast run, and we were able to validate the results amongst these nested tiles. The two configurations, so every year, as part of our HFIP, we run real-time experiments. These typically start 1st of August and last through 1st November to coincide with the active time period of the hurricane season in the North Atlantic Basin. So for year one, for FY19, we had two configurations which were set up in real time. The two are shown here. Version 0.A on the left is a static 3-kilometer nest covering area of interest in the North Atlantic Basin. On the right is HAFS version 0.B, which is a very similar static nest at 3 kilometers within in the North Atlantic, but this is nested within a global FV3. And both, so which was at 13 kilometer, which is the same resolution and same configuration as our FV3 GFS system in operations. Here's an example of some early success using the HAFS 0.A version. This is for Hurricane Dorian in August, September of 2019. This version, as well as other HAFS versions, were able to pick up on the right turn of Dorian once it went past Bahamas and actually stalling near Bahamas. And it was able to pick up on this right turn much sooner than our operational models. So this was an early example of success with our HAFS approach. Here are some results, overall results for the North Atlantic 2019 season, comparing HAFS-A and HAFS-B with our operational models, HWRF, HMON, and as well as GFS. And we got good improvements in track error, reductions in track error using HAFS versions. Both HAFS-A and HAFS-B are very similar. And we were happy to see better track scale from HAFS, shown in the track scale plot in the upper right, as compared to operational models. But in terms of intensity, we found that there's quite a bit of work to be done. We had large initial intensity errors for both HAFS configurations. This was primarily because we were spinning up, we were doing cold starts, so we didn't have any formal initialization procedures nor data assimilation. And the errors reduced after, say, 6 hours or so, but then continued to increase further. We were happy to see that by day 5, the errors were reduced as compared to the operational models, but still lag behind for the rest of the lead times. And both HAFS versions 0.10 and 0.B were very similar and comparable in their intensity forecast. Moving on to year 2. In year 2, some of the highlights which we have worked on, developed, so this is now FY20, is to introduce coupling with an ocean model. We've been working and now have some functional data assimilation for HAFS. We have workflow enhancements, accounting for the coupling with ocean model, as well as other enhancements for including data assimilation. There has been quite a lot of good work recently on having the ability to have moving nests within FV3 dicore. And just like year 1, in year 2 also we formulated and tested multiple HAFS configurations, and some of them are listed here. We introduced a regional static nest with ocean coupling, which is version 0.1a. We persisted with the regional nest within global FV3, version 0.1b. We introduced regional ensembles, and as well as looked at alternate regional grid projections. I'll be discussing all of these configurations in a little bit in some more detail later. So as I said, we introduced coupling. So this year we used in real time a regional formulation of HAFS, which was coupled with HICOM. And we're using the NEMS infrastructure. NEMS stands for NOAA's Environmental Modeling System, and is the infrastructure being used in UFS applications for coupling, in all applications for other use as well. Here the coupling was achieved by using connectors with NEMS driver, and listing of all the variables which are passed from atmosphere to ocean is shown here. All the surface fluxes from the atmosphere were given to the ocean model, and in turn, ocean model gave sea surface temperature information back to the atmosphere. So we had to introduce coupling in our workflow. We used RTOS, which stands for Real-Time Ocean Forecast System, with operational global ocean model to set up our initial and boundary conditions for the ocean model coupled to FV3 within HAFS. And we designed it in a very modular fashion, which allowed us to run the same system with coupling or no coupling, or changing how we are doing our interpolation. One other aspect which we which I indicated earlier is important, is the vortex initialization process. Based on our experience with building HWRF and HMON in operations, having good vortex initialization is key. And one method which we've been exploring as part of HAFS is a GSI-based tropical cyclone relocation method. And some details of this method are shown here, whereby we use the 6-hour forecast field from the model to create synthetic profile type observations. And then these observations are then relocated or recentered based on the current known location of the vortex, and then these are assimilated using GSI as synthetic ops or ops to help locate or relocate the tropical cyclone. We've also been working on data assimilation capability within HAFS. Right now, some of the features are shown here along with the schematic. So we start with the GFS analysis, and then we do a warm start for the current forecast cycle using forecast state from the previous cycle. Perform a GSI-based TC relocation, which I just described, and then we have a 3D VAR-based system, DA system, to assimilate other ops, and we deploy a 6-hourly hybrid 3D NVAR approach using GDAS, the Global Data Assimilation System Ensemble, for our hybrid DA. As I mentioned earlier, a key or critical part of HAFS development is to build moving nest capability within FV3. And here are some of the recent developments involving that. So currently we have the algorithms to move all the prognostic variables. And along with it, all the diagnostic variables can be recalculated. We've been able to do 6 stable runs with our current algorithms for dynamics and also full physics, along with two-way feedback. And we have been testing this over the open ocean, and some more work remains to be able to test it over land as well. But recently there has been a lot of good progress here. All right, so as I mentioned earlier, every year we use our HFIP real-time experiments. I've been using those for HAFS model as well. And these experiments tell us a lot about the skill, as well as give us very good information on what's working and what needs further improvement. So just like year one and year two, we had primarily four different real-time configurations which were tested, starting with 0.1A. This is our regional FV3 shown in the schematic in blue, covering the North Atlantic Basin. And this year we coupled it with HICOM, which is shown in red. We adjusted the domain size and added some more vertical levels, 91 vertical levels this year. Also experimented with quite a few of the physics options, which are listed here. We used GFS, operational GFS, for our initial and boundary conditions, and did 5-day forecasts. For the ocean model, HICOM, we initialized those with the conditions from RTOS, and used methods to merge information with the non-overlapping regions for both the atmosphere forcings for the ocean model, as well as conditions of SST information back from the ocean to FV3. One other configuration which we persisted with, like year one, was the 0.1B. This is our regional nest within global FV3, as shown here. in the schematic. This is the tropical channel global layout of FV3. For this configuration, we ran our experiments out to 7.25 days so that we could provide 7-day interpolated forecasts to those and give those in real time to our forecasters at NHC. And the one advantage of using a global domain is that it also allows for direct comparisons with the operational GFS and assess the impact of the nest on the global domain and the two-way feedback. The physics and dynamics options were similar to version 0.b we used in year 1, though some upgrades were made to PBL physics. One other configuration, 0.1J. This is again a regional HAFS, but with a different grid projection. The ESG projection stands for Extended Schmidt Mnemonic. The idea here is to have a more uniform grid. If you look at the bottom panel, which shows the contours for the grid size in 0.1A in traditional FV3 regional configuration, the grid size can vary quite a bit from the center of the domain to the edges. So this projection gives us a more uniform grid, as shown in the bottom right panel. And one other advantage of this is that it reduces our computational cost. We tried this as well in real time. And one other configuration which we also looked at in great detail was having an ensemble system, a regional ensemble system. So we introduced an 18-member ensemble system, 1 control and 17 perturbed. To be able to have so many members, we had to reduce the resolution. So all other regional configurations were at 3 kilometers. But for this, we use 6 kilometer and also use 64 vertical levels instead of 91. There's some changes to the physics, especially for cumulus parameterization. For the initial condition, boundary condition perturbations, we used GEFS, a global ensemble forecast system, GRIP2 files, and introduced some stochastic-based model physics for the various members, which included things like stochastic kinetic energy backscatter, stochastically perturbed physics tendencies, as well as stochastically perturbed PBL humidity. So here's our performance assessment of all these different configurations. Here I'm showing for the North Atlantic Basin. All the results are in skill space being compared to the operational HWRF. And what we found was that a HAFS-B configuration, which is the nest within a global FV3, had the best track scale, shown by the green line on the left panel, followed by the HAFS-J, which is the uniform grid, and HAFS-A, both regional configurations, J and A. But if you look at the right panel, which is the intensity scale, we find that all HAFS configurations lag behind operational HWRF, especially for the early lead times. HAFS-A and to some extent HAFS-J caught up to operational HWRF for the later lead times beyond day 3. But overall, the HAFS configurations did better for track compared to operational HWRF, but not so much for intensity. This is now looking at the EPAC storms, and similar story. For track, all HAFS configurations did better, especially HAFS-A and HAFS-J. Both of them had the best track scale, followed by HAFS-B. But for intensity, all of them lagged in intensity scale as compared to operational HWRF. So this gives us an idea that you need to focus on how to catch up to reduction of intensity errors. That's the main challenge going forward with HAFS. Here I'm comparing the performance of the ensemble system, 0.1E, compared to others, as well as operational HWARF. Again, for track, the ensemble system had comparable track scale to HAFS-A and HAFS-J, the two regional domains, till around day 3, but was lower thereafter. For intensity, actually, the ensemble system had the lowest intensity errors, especially for extended lead times, that is past day 3. So days 3 to 5, the intensity scores are very good with the ensemble system, and that's shown by the green curve here. All right, so we've done all this work. We know where we're doing well. We also know where challenges remain. So keeping all those in mind, and also keeping knowing or repurposing our knowledge of the existing operational systems, HWARF and HMON, we have some initial targets for the operational capability for the first version of HAFS. We are targeting FY22 for having the first operational implementation for HAFS right after the moratorium. So some of the guidelines for us include maintaining current CONOPS, or concept of operations. So currently we have 5 maximum storms in the NHC area of responsibility, namely the North Atlantic, East PAC, and Central PAC basins. So we can run 5 storms for both HWARF and HMON in these basins. And for HWARF, we have maximum 7 storms, which can be run concurrently in all global basins. So this includes not just the NHC's areas of responsibility, but also JTWC, which is North Indian Ocean, Western Pacific, and the Southern Hemisphere. But in total, we can run maximum 12 storms concurrently in current operations. And some of the other functionality which we are targeting for the 2021, or in time for the 2021 hurricane season, is to build up and then fine-tune our formal vortex initialization. We could use GSI-based methods, which I discussed, or our traditional vortex modification methods, which we have been using for both HWARF and HMON. We already have coupling with ocean, but we need to build that out further, more on that later, with HICOM, and also introduce at least one-way coupling with waves, or at least have the infrastructure. This would also allow us to test 3-way coupling between the atmosphere, ocean, and waves at a future time, to build our data assimilation capability. And then to account for all of these developments, we have to make workflow enhancements, which allow us to use all these different modules. And of course, as always, all decisions on our IOC and whether it goes into operations will be based on the science evaluations to be done at TMC and NHC. So here's our target option 1 for HAFS IOC. So here we are envisioning moving nests, single moving nests. So these are storm-centric moving nests which follow the storm vortex. This is very similar to how we do current HWARF and HMON. And here we are targeting having outer domain at 4.5 kilometers and embedding moving nests at 1.5 kilometers. With GFS version 16, which goes into operations early next year in February, we will have 127 levels. So we will have to figure out how many vertical levels we need for HAFS. We've been testing with around 90 or so, with good results. And here, depending upon how much more computational, how many more computational resources we can get on the new WCAS, we can target up to 12 different concurrent storms using this configuration. This would mean that we have 2 variants for HAFS, in the NHC's area of responsibility. For this configuration, we, as I mentioned before, still have a lot of work ahead for vortex initialization, coupling with ocean, and we want to use CMAPs, more on that later. And for data assimilation, we would need to build up our capability to do dual resolution data assimilation using hybrid 3D and VAR methods, and ideally do subcycled data assimilation, which is very similar to our current operational HWAF. Our backup target for HAFS-IOC focuses on static nests instead of moving nests. So here we envision having two separate domains at 3 kilometers, one covering the North Atlantic domain, as shown here in the schematic on the right, and another similar configuration covering EPAC. For this also, we would need to work on vortex initialization, coupling with oceans, and for data assimilation, we'd like to have a hybrid 3D and VAR system, which is self-cycled. This backup configuration would allow us to replace either HWAF or H1, but probably not both. So some of the ongoing developments for HAFS include leveraging other developments happening for other applications within UFS, both the global as well as for the CAM group, the DA developments. We continue to build out and enhance our workflow. We're using a modular approach, which allows us to easily turn off and on different aspects of the HAFS system. Moving nest algorithms are being worked on, both in context of having that capability for FV3 dynamics as well as for physics. We are looking at accelerating our ability to do a good job of initializing the hurricane vortex and its environment, both with advanced DA methods. This is work ongoing for now, will continue for the next few years. And some of the things we are looking at is looking at new data to be ingested with better quality control methods, which allows us to admit and ingest more data, more information, as well as explore new DA algorithms and technologies for inner core or the vortex scale data assimilation. We continue to work on looking at different physics options. These include all aspects of physics, ranging from PBL, microphysics, radiation, surface physics, and of course, also then looking at the interactions between these different options, different schemes, and conduct experiments with all these different options and advances, and look for improved analysis as well as forecast scale. So talking about physics specifically, so we are using looking at all available physics suites in CCPP. CCPP stands for Common Community Physics Packages. These are available to all UFS-based applications, as shown listed here. Even recently, with help from TTC, H4 physics has been added as an independent suite within CCPP, and we've started testing with that as well. As I mentioned, we continue to do both dynamics and physics experiments. Here is an example for Hurricane Michael. Here we were looking at different horizontal grid resolutions and their impact on the forecast scale. And for this particular cycle, on October 7th, 2018, the 18Z cycle for Michael, we see that even though for track, we're doing a pretty good job already, but for intensity, having a 1.5 kilometer resolution gives us the best intensity scale, as shown by the yellow curve on the right, as compared to coarser resolutions. For coupling, we already have coupling, as I discussed, using connectors within the NEMS framework. But to remain in step with other coupling developments within UFS, We recently introduced the CMEPS mediator. CMEP stands for Community Mediator for Earth Prediction Systems. This is a modern, much more modular and efficient mediator which has been built in collaboration between NOAA, NCEP, and NCAR. And so this mediator has been introduced within HAFS, and we envision using this going forward to do coupling between the atmosphere and the ocean, as well as adding waves for full three-way coupling. And here's a schematic showing how the information will be passed via the mediator to different Earth system components within HAFS. For DA, here's a schematic of how we envision the future DA system to look like within HAFS. So the lower half of this figure is already been worked on and is functional. The upper half introduces a ENKF system, which allows us to use both, starting with the GDAS ensemble, and then repurposing those for perhaps a self-cycled or a partially cycled system, whereby we use the ensemble information for having flow-dependent covariances and in doing improving upon our initialization. This is similar to how we have been using DA for our operational HWRF. So we have quite a bit of experience with it, but we are building this for HAFS, very similar capability. A lot of work remains to be done, but this remains a goal for us. I also wanted to talk a little bit about the connections between HAFS and other UFS projects. So these include the Hurricane Supplemental projects, as listed here, includes connections to other UFS R2O projects. And apart from this, we also have a lot of other collaborations from these different UFS application teams, as well as different working groups and the Joint Center for Data Assimilation. Here's the same information depicted in a strategic roadmap, showing the various modules on which we are leveraging UFS Global and LAM CAM developments, also leveraging UFS infrastructure developments, and in yellow here are the ones which are the core UFS HAFS developments. So for the next 3 to 5 years, as I said, we hope to have initial operational capability by FY22. And the idea would be to replace existing operational HWRF and HMON with HAFS when the performance and deliverables meet requirements of the relevant stakeholders. Continue our advancements in vortex initialization, data assimilation, physics, and coupling for FY23 and beyond to improve upon the initial versions of HAFS. And then for the future, to embed these moving nests and regions within the global UFS system with complete two-way feedback between the nest and the parent domains. And this is a long-term vision where we envision HAFS developments, making it into a combined HAFS GFS system, whereby we can follow the vortices with moving nests within the global UFS application. Thank you. We'll take some questions now.
Thank you. There is one question in the question box. When will the HWRF and HMON be removed from operations and be replaced with HAFS in operations?
So like with everything, with all our applications, all our operational systems and products, decisions are based on evidence. So when HAFS versions or HAFS configurations satisfy our stakeholders, satisfy our forecasters that we are doing as good a job as HWRF and HMON, only then HAFS to be considered as a replacement for those systems.
Avichal, I have a question. You have shown the HICOM has been coupled with the atmosphere for the real-time experiments this year. Is that coupling includes in all of them, A, B, and J, or only in A?
Right now, Jan, it's only for our configurations we tested this year, it was only for A, the regional nest, but the same coupling can be repurposed for all other configurations. And also in terms of choice of ocean models, right now we picked HICOM because HICOM has nesting capability and DA capability. But the long-term plan, for especially in the 3 to 5 year time frame, is to swap out HICOM with MOM6.
Is there a way to identify or to insert the impacts of the ocean, the coupling, compared to A with other experiments?
Yes, we looked at that specifically when we added coupling this year. I don't have the results here, but I can share those with you, Jan, separately, whereby we did see improvements when we added coupling in our HAFS-A configuration for this year. And track, it was mostly neutral, but for intensity, we did see improvements in both bias and reduction of intensity errors. I can share those results with you.
Oh, great. Great to know. Are there other questions? Folks, you should be able to unmute yourself. Just ask a question, or we can unmute you. Right? Anyone want to ask questions directly? You should be able to unmute yourself. Yeah, I have one more question. Avichal, in the results you have shown the operational GFS, is that GFS version 15? That doesn't have a good skill, looks like, compared to other runs. I'm just yes, that's the one. Avichal, we cannot hear you.
Can you hear me now, Jan?
Yes. Mm-hmm.
Okay, so yeah, so the blue here is operational GFS, and actually it did quite well for track. It did better than operational HWRF and is quite comparable to the other HAFS versions, only behind HAFS version B. And for trying to go to, yeah, and for EPAC as well, as you can see, the operational GFS for track did quite well. For intensity, usually the regional hurricane models like HWRF, HMON, they do a much better job as compared to GFS because of their high resolution and ability to resolve the structure of the vortex.
Can you go to the previous slides for the Atlantic Basin?
Yes.
The previous one. Yes, this one is showing the intensity forecast from the operational GFS.
Yes,
at the beginning, it's very low, right? Okay.
Yeah, so global models cannot capture the entire structure of the vortex, Jan, because of their resolution.
Yes. Okay.
Right? So the global GFS, that's 13 kilometers. HWRF is 1.5 kilometers for the innermost vortex. So the regional hurricane models always are ahead in terms of intensity scale compared to the global model.
Thank you. Are there any other questions? All right. Yeah, I'll try to fill up the time. Okay, so Avichal, do you think the track scale, the nested, the global one, has some advantage over the static?
Yes, as shown here, by this green line here, when we put a nest within the globe, it had the best track scale, and that makes sense because that way we are able to resolve or get the most updated information for the nested region from for the rest of the globe, rest of the environment around the storm. So one of the reasons to try a nest within the global model is to actually achieve much improved track scale. So that result is expected, and we were happy to see that.
So that using the information from the global GFS during the
no, it's running with its it's running with its own global model. So
okay, all right.
The nest and the globe are in a way exchanging information as they both integrate together.
I think that's great. Sorry, I've been trying to fill up the time. If there's no more questions, we can call it. Thank you, Avichal, for the wonderful presentation. Thank you for everybody to dial in. You can write email to Avichal afterwards. You have if I have your other questions. The recording will be available at the UFS portal, and also the slides will be available too at the UFS portal. Thank you, everybody.
Thank you. Bye-bye.
Okay, bye-bye.